So we will have a break for the next 30 minutes and we'll be in the breakout rooms. There are 6 breakout rooms. Number 1 is persona, number 2, data mobility, number 3, science DMC, 4, routing policies, 5, number 5, network security, and 6, programmable switches. Christy, I don't know if these rooms are already open.
They are ready. I'm going to pause the recording.
Okay, we're gonna start our last hands-on session of this conference workshop. So Ali will be presenting, going through this hands-on session number 4, local preference and MED attribute. We're still talking about BGP. So Ali, do you want to start this session? Go from the enroll and then start the lab?
Yeah, sure. Do you want me first to start the presentation and then I'll do the enrollment for the hands-on session?
No, you can start the presentation. I will let you lead this as you prefer.
Okay. So I'll share my screen. Okay, so now we're in the hands-on session, local preference and the MED attributes. You can find again the PowerPoint and the PDF here. This is the PowerPoint overview that I will be using for this hands-on session. And so I'll just go briefly an overview of the BGP attributes and how BGP selects the best path. And basically, there are multiple attributes that BGP uses to select the best path when there are multiple paths to the same destination. In this hands-on session, or in particular in this lab number 8 that we'll be covering, we will talk about the local preference attribute, as well, which is point 2, as well as the MED attribute, which is point 6. But there are other BGP attributes. Some of them we also cover in other BGP labs. Essentially, without any advanced BGP configuration or without route manipulation, BGP selects the path which has the shortest autonomous system path attribute, which means it chooses the path that has the least number of AS autonomous system hops. However, if you're a network administrator and you want to route the traffic through a different path, you have some BGP attributes such as the local preference and the MED to influence incoming and outgoing traffic. So what is the local preference attribute? It basically indicates to routers what is the preferred way to exit this autonomous system. And the higher the local preference value, the better, or it has a higher precedence. So in this example, as we see on the right hand in this topology, we have network autonomous system 64520 that receives routing updates from 172.168.0.0 through 2 paths or 2 directions. The first one is through autonomous system 65500, which is only 1 hop away, 1 autonomous system away. And the second one is through two autonomous systems, 65000 and 65250. So again, without route manipulation, as I mentioned, the autonomous system will choose the path with the least number of autonomous systems, which means this one. However, you can configure the local preference within this network itself, so that this route or this direction has a higher precedence over this one. So in particular, you can configure the local preference on router RA so that it has this path has a local preference 200, and this on router RB, this path has a local preference 150. So now the information will be advertised through all the routers, and this network will be selected to to steer the traffic from AS Autonomous System 64520 to this network. All they will be sent out to router RA as an exit point from this network. So the local preference is intended to influence all outgoing traffic. But however, what if you want to influence incoming traffic to your autonomous system or to your network? In this case, you will use the MED attribute, which indicates to external neighbors what is the preferred path into autonomous system. So in this scenario, let's say that you are the network administrator of autonomous system 65500, and you want to influence all incoming traffic from this autonomous system AS65000 through the link connecting router A to B. You will need to configure the MED attribute within your autonomous system, in particular in a router RB and RC, so that the lower the MED attribute, the higher the precedence, which is in contrast to the local preference attribute. So in our case here, we configured the MED attribute on this link to be 150 and on the other link to be 200. So now all the traffic from network autonomous system AS65000 to 65500 will go through the link connecting A to B. And some use cases that you wanna why would you wanna change the like the path, incoming and outgoing traffic, is sometimes you could have like a higher bandwidth primary link, as we will see in our lab topology. So in this hands-on session, we will be covering lab number 8. This is the topology. You have two networks, two autonomous systems. The ISP has autonomous system 100 and the campus network has autonomous system 200. And as you see here, they're connected through a primary link and a secondary link. And our goal is to route all the traffic exchange between these two autonomous systems through the primary link. Unless this primary link fails, so that's when the secondary links come in handy. So to do that, we'll configure the local preference and the MED attributes. And this is just a brief configuration that I will go into details in the lab. For configuring the local preference attribute on R2 and R3, you will establish a route map, you will set the local preference, and you will attach it to a BGP neighbor. And similarly, you repeat the same local preference configuration on R3 with modifying the local preference value to be lower, because you need the primary link to be the one that will be used by default. Now, after you configure the local preference, we'll also check the BGP table of the routers, so that now R3 is, we will notice that R3 will no longer use this path, but rather it will use this path, which goes through the primary link. And similarly, now to influence all the incoming network traffic from the ISP, you will configure the MED attribute in a similar manner to the local preference attribute. And you will see how the ISP will be affected by the MED attribute, so that when it routes traffic to 192.168.3.0, it will choose the primary link rather than the secondary link. So we'll go over this in details in our hands-on session. Again, to get into the pod, you can click on the enroll here. you will see the set of BGP labs in case you've already enrolled into it. For me, because I'm already signed in, it will immediately show this. I'll go ahead and choose lab number 8. Just be aware, because there's lab number 8 and lab number 8.1. We're only focusing on lab number 8. So I'll click to make a reservation. Just take a few seconds to initialize. Okay, so again, here's the content of the lab. I'll go ahead and open it. Just split the screen into 2. And on the right-hand side, I'll be using the pod. Again, this is will be proceeding the similar way as I was doing in the first hands-on session. Here you will see the overview, objective, lab settings, password is password. This is an introduction if you want more information about the BGP labs. And this is our topology. I'll be starting from section 2.2, which is opening a mini edit. Here, the password is password. Again, I will load the topology. It's already there. I will just load it, the topology of lab number 8. Click on File, Open, lab number 8. Select the end topology. And now I will load the IP addresses because I don't want to configure them manually. So I'll just launch a script that will do that automatically. You'll need to open a Linux terminal, the right icon to the third icon to the right. Go to the directory, which is lab number 8. You will execute the command to load the IP addresses. And in this case, and I will exit because I no longer need the Linux terminal. Now, when the IP addresses are loaded, I can go ahead and click on the Run button here so that the emulation starts. Again, if you want to check the links of our topologies, you can just write here links. And you will be able to verify which every device to which interface is connected to which other interface, which other device. Now, similarly here, you can verify the IP addresses of the hosts, H1, H3, H2, so on. I'll just skip over that because the IP addresses are already configured. Can similarly verify the routing table of host H1, H2, and the default route of H1, H2, and H3. Now, moving to the routers, I will have to do this. Hold the right click on R1 and select the terminal. I will launch the Zebra daemon and enter the VTYSH session. Now I'm in the FRR shell. You can verify the routing table of R1 and just to validate the IP addresses are already configured correctly. using the script that we launched earlier. Similarly, this step is necessary for every router to enable the Zebra daemon. So I'll go ahead and do it right now. Zebra VTYSH show IP route just to validate. Similarly, on R3, hold the right click terminal, Zebra VTYSH show IP route. Now I've launched the Zebra daemon, validated the IP addresses. I'll move directly to the BGP configurations on the router. So we'll begin with router R1, and because R1 is in a different autonomous system than R2 and R3, then we'll be configuring Ebgp. But it's the same configuration, just like a different terminology, Ebgp and Ibtp. So we'll go to router R1 here, click on it. I'll exit to the Linux shell to enable the BGP daemon. And I will go ahead and go into the VTYSH session. Now I'm in FRR. Go to configure terminal. And now I'll be assigning the autonomous system number of router R1, which is 100. So to do that, you write the command router BGP 100. It's the same configuration so far as we've done in the previous hands-on session. Similarly, we'll assign a router ID for R1, and we're following the same convention. BGP router ID 1111. We'll establish a BGP neighborhood first with router R2. Router 192.168.12.2 is this one. So now R1 is establishing BGP neighborhood with R2. Neighbor, specify the IP address 8.12.2 and the autonomous system of your BGP neighbor that you're peering with, which is 200. Refers to the campus network. Now, similarly, R1 is also connected to R3, so we need to establish a BGP neighborhood with R3. So the same command, different IP address, neighbor, IP address of this link, 192.168.13.2, and the autonomous system of the neighbor, which is also 200. Because R2 and R3 are in the same autonomous system. Now, R1 will need to advertise its network so that R2 and R3 know about 192.168.1.0. So to do that, the command is network 192.168.1.0/24. Now I will exit the BGP configuration mode. And I will check the BGP table just to make sure that this network is advertised through BGP. So the show IP BGP. And here you'll see that the network 1.0 has been advertised. It's locally advertised. I just went over this fairly quickly because we already did the same steps in the previous hands-on session. And similarly, now we're configuring Ebgp and Ibtp on routers R2 and R3. And while we're Ebgp is going to be between autonomous system 200 and 100, and Ibtp is going to be between R2 and R3. So I will go to R2 terminal now to configure BGP. Before that, you need to enable its daemon. So you will go exit the Linux shell, BGPD to enable. That's step number 2. Go back to VTYSH session of entering FRR and configure terminal. Assign the BGP, or what is the autonomous system number of R2? It's 200, router BGP 200. Same, and assign a BGP router ID for R2. So it's BGP router 2.2.2.2. And similarly, I will be establishing a BGP neighborhood with R1 and as well as with R3. So first with router R1, the neighbor command, the IP address 192.168.12.1, which is this one, and the autonomous system number is 100, corresponds to R1. Similarly, the neighboring command for Ibgp is the same. You also write neighbor 192.168.23.2, and the remote autonomous system is the same as the router R2, which is 200, because they're both in the same autonomous system. Now, step number 9, you will be advertising the network. And router R2, it will advertise the network 192.168.2.0, as well as the external network. So the step number 9, you're advertising R2 is advertising its internal network 192.168.2.0/24. And it will advertise network 192.168.12.0/30. And the reason why we're advertising this network, because R3 here does not know about the primary link over here, right? Because this is the primary link and this is the secondary link. So in order to for R3 to know like have an entry to the primary link in its routing table, you need to advertise it by router R2. So now we configured BGP on R2. We can exit the BGP configuration mode using the command and similarly, we will repeat the same BGP configuration on R3, which establishing BGP neighborhood and advertising the networks. So I will go to router R3 here. We'll exit to the Linux shell. I will enable BGP daemon, BGPD. I will enter back to the VTYSH session, which allows me to configure BGP. Configure terminal, router BGP 200, autonomous system of R3, and assigning a BGP router ID 3.3.3.3. Establishing a BGP neighborhood with first R1, which corresponds to 13.1. And one thing I didn't comment on is the IP addresses. The convention that we use is like 192.168.168 is fixed, and then the second one corresponds to the indices of the router. So for example, the link between R1 and R3 is 13, and then R1 has .1 and R3 has .2. Like the lower, it will take it incrementally. So this is the convention that we use in all our lab for simplicity. Now back to establishing a BGP neighborhood. Neighbor 192.168.13.1, remote autonomous system 100, this one. And the next neighbor is R2. So the IP address would be 192.168.23.1, a remote autonomous system 200. And R3 will advertise two networks. First, its internal network 192.168.3.0 here. And the second one is 192.168.13.0. So that R2 knows about this network, knows about this secondary link. If you didn't advertise this network here, the external one, like someone would say, why would you advertise external network? Otherwise you would need like an IGP inside your like campus network, so that R2 knows about the secondary link and R3 knows about the primary link. And in fact, in lab number 8.01, we have, like, instead of advertising this network, we have an IGP like running, OSPF running within this network. So if you want to have a look at it. So back to advertising the network, the first network is 192.168.13.0/30. And the next network is 192.168.3.0/24. Okay, now that we have already configured BGP on R1, R2, and R3, I'll exit the BGP configuration mode on R3. And I will check the BGP table. So show IP BGP, just to see what are the modifications that happened so far. And as we see here, I think I will. Okay. Might have. So on R3, as we see here, there's the R1 is through 192.168.13.1, but the other one is not run. I think I maybe made a mistake here.
Your neighbor statement was a typo.
Oh, sorry. I will go ahead and just fix it. BGP 200 neighbor 192. I forgot the dot. 23.2 remote autonomous system 200. Okay. Let's hope now it's working. Okay, perfect. Thank you. Okay, now after displaying the BGP table of R3, we will see here that router R3, in order, let's look into this entry, these two entries. So the network 192.168.1.0/24 has two paths. The first one is through the next hop 192.168.12.1, which is this one, through the primary link, and the second one is through 192.168.13.1, which is directly connected to R1. And to see which one BGP is using, we can look into the arrow sign, and here the arrow sign indicates that this is the best path. So the best path that is basically used to reach the network 192.168.13.1 .1.0 is the secondary link. And why is that? I just will go back a little bit to the BGP attributes that I mentioned. And so far we haven't configured any BGP attribute. And by default, if you see here number 7, the BGP prefers the external path over the internal path. So here, this path 192.168.1.0 has been advertised internally through 192.168.12.1. So the primary link is advertised by R2, and the secondary link is advertised externally by R1. So by default, R1 will choose this path. But as we mentioned, our goal is to configure BGP local preference so that R3 all the network traffic from the campus network will go through the primary link. So we will do that in the next step, which is focusing on the local preference attribute. And as you see here, the local preference haven't been changed. The path is 100i because you need one autonomous system to reach it, and same here, same as here. Now we need to configure the local preference, as you said. We'll go to router R2 first. Go back to configure terminal. And I will set a route map, which is basically route map is like a permit clause, or you can say it's like an if-else condition, allows like more programmability for the router. And I will use it to set a local preference for this route. So you write route map, and I will call it primary N because just like naming convention, primary N, and the permit, and you will assign a sequence number 10, which is the default sequence number. Next, within this route map, you will set the local preference attribute. So here in this lab, we set the local preference to 150, and that's for the primary link. So eventually, the secondary link should have a lower local preference value. So set local, I just click on the tab to auto-complete it, and we'll set it to 150. Now you can exit the route map configuration by writing exit, and you will go back to the BGP configuration so that you assign this route map to the neighbor. Now router BGP 200 to enter BGP configuration mode. And in this step here, what we're doing is we're attaching this route map, which is called primary N, that we have created here, to the neighbor R1. And we're doing that because we want to set the local preference attribute to attach it to this neighbor, or basically to this path. So you write neighbor 192.168.12.1 route map, and the name of the route map, which is primary N, and you write N because you're basically referring to like the influencing incoming traffic. Now I'll exit the BGP configuration mode and I will repeat the same steps on R3 and set the local preference of this path to a lower value so that this is the primary and this is the secondary. So I'll go to router R3 first configure terminal, and I'm following here the steps summarized in number 8, step number 8. Create a route map. I will call it secondary N. You can call it whatever you want. And permit 10 again. Set the local preference. We're setting it to a lower value because we want it to be have a lower precedence. I'm setting it to 125. Now exit the route map configuration. Enter the BGP configuration, router BGP 200. And now the route map that you created here will be assigned to the neighbor R1 as follows. 13.1 is R1. Sorry. Route map secondary N. Same configuration, and I'll exit. Now, to verify that, like, let's see, now we've configured the local preference attribute. In order to verify that, let's check the BGP table of R3 and see if there are any changes. Show IP BGP. Okay. So now this entry here, 190, this network address 192.168.1.0. If you notice, the arrow here has moved from here to here, and this means that now, in order to reach this network, you will use the next hop 192.168.12.1, which is here, which is this network, this address. So now, if router R3 wants to send any traffic to this network 1.0, it will use the primary link. Again, the local preference here, you will see that now it is set to 150, and for the next hop, the primary link, and it's set to 125 for the secondary link. So all the network traffic now from R2 as well as R3, because R2 will by default use this primary link. R3, after configuring the local preference attribute, will use also the primary link. And we will also test that later on. Okay. Now we've achieved like the first goal of our lab, which is basically steering all the traffic from the campus network autonomous system 200 throughout the primary link. However, what if we want to also, like, what about the incoming traffic from the ISP or autonomous system 100? Let's see what's happening here. So here, let's go to router R1. And you will show the routing the BGP table of R1. So let's see here what's happening. Basically, let's look more specifically onto this network, 192.168.3.0. Let's see what's happening. R1 here will use, in order to reach the network 192.168.3.0, it will use the next hop 13.2. And that's, you can see it from the arrow sign over here. So what we want to do is basically make R1 steer all the network traffic through the primary to 192.168.3.0 through the primary link rather than the secondary link. So we'll go back to R2 and configure the med attribute. Configure terminal. It's similar to the local preference attribute, by the way. We'll create a route map. Route, this is for the med attribute, primary med. And you will assign a value for the med attribute. And here, in contrast to local preference, the higher the value, it's the better. So here will be set to 50. You will exit the route map configuration. And now we'll go back and assign it to the neighbor. So neighbor 192.168.12.1 is R1 route map primary med out. So this is the route map that we created, and this is out is to refer to all the outgoing traffic. So we'll hit the enter. Now the route map is assigned to our neighbor. Similarly, I'll repeat the same process on R3 to see what are the and see what are the changes. Now, again, configure terminal, route map, secondary, permit 10, and because as we said, the med attribute, the lower the better. So in this case on R3, it needs to set the local the med attribute to a higher value. Here we'll set it to 75. And we'll hit exit. Now, after initializing the route map, I'll also assign it. And let's attach it to our neighbor, 192.168.13.1 route map, secondary med out. So with that, I've configured the med attribute on router R3, and on router R2 we assign it to 50 so that this link has a med attribute 50. On router R3 we assign it to 75, and as we discussed before, the med attribute will influence all like external autonomous system. So even though we let's say if we are a network administrator in campus 1, we don't have to have access to autonomous system 200 or the ISP in order to steer the network incoming traffic to our autonomous system, but rather from the network itself, we can do that throughout the med attribute. So that's why we didn't configure anything on R1, and we only used R2 and R3. So I'll just pause for a few seconds if anyone has any question or comment on the local preference or the med attribute so far. Okay, it seems that there are no any question or comment. Okay, now after configuring the med attribute, I'll go ahead and verify that it's now working. So how do I validate that? I go to router R1 and I make sure that R1, when it steers the traffic to 192.168.3.0, it will take the primary route, which is through R2, rather than the secondary route, which is through R3. So I'll go to R1. Let's show the BGP table. And here, you will see now that, where's the network? Okay, here it is. You'll see that the network 192.168.3.0 will have the next hop as a preferred one, 12.2, which is this router. And you see here the meta attribute is 50 for the next for R2 and 75 for R3. So now all the traffic from this network ISP 1.0 to 3.0 will go to the primary link. And we'll also validate that through another method. I think there's a question here. That's the entire router. Does the entire router need to be assigned to an autonomous system, or you can specify the interface? In our configuration, we are assigning the whole router for an autonomous system. But I believe if you have multiple routing tables, which is through VRF, then you can assign it to a specific interface. But we're not doing that in this lab series. I can check that here really quick. Router BGP. Oh, you can see here there's the VRF option where you can assign like to which VRF table that you wanna, like in case you're using VRF. Anytime. Okay, so now we'll do the last test just to verify that our configuration is working, and now the traffic incoming and outgoing from AS100 to AS200 is only through the primary link. I will go to R3 and I will perform a trace route. So just end. So the trace route command enable you to like see what are the hops that the packet is going through. Specify the source 192.168.3.1, which is corresponds to this network, and what is the destination 192.168.1.10. And here, as you see, the route or the path that the packet takes from this network 3.0 to 1.0 is first through 23.1, which is this hop, and then 12.1, which is R1, this interface, and then reaching to the destination, which is 192.168.1.10. So now with the trace route command, as well as the route, BGP and table, we've verified that our configuration is working. We verified that using these two commands, we can steer the network traffic as we wish in the network. But the last thing that I want to comment on is, what if the primary link fails? So will the secondary link come in handy? And that's what we'll try. So we'll go to R1. And I will shut down the interface R1 ETH1, which is the primary connected to their primary link. So I'm just like emulating that the primary link is down. So interface R1 ETH1. And the command to shut it down is shut down. Let's see how the traffic is now steered. and just check the BGP table again one more time. And here, you will see that the two networks now, 192.168.20 and 3.0, they will only have the next hop 13.2, which corresponds to the secondary link. And that's expected because we have shut down the primary link, or basically emulated that it's down. So we'll also do a trace route test. Same, I'm still in R1, exit to the Linux shell. Trace route. And as you see here, in order to go to even this network here, H2, there's no way that you will be using the primary link. However, you will be using the secondary link 13.2, and then from 13.2, you will be able, it will forward it to R2 and then to the final destination, which is 2.10. So with that, we conclude our lab. To sum up, we learned how to we learned about the local preference attribute that basically influences all the outgoing traffic within the autonomous system. And the local preference attribute, one thing I haven't mentioned, is not advertised to external autonomous system. So it's only advertised within the Ibtp neighbors. And that's how R2 knew that this is the primary and this is the secondary, and similar for R3. We also tested that using showing the BGP tables. Moving forward, we configured the MED attribute so that now all incoming traffic from external autonomous system will follow the primary link as well, rather than the secondary link. And the difference between MED and the local preference, like this one difference, is that the MED is shared with external autonomous system, like one hop away. So that's how it allows us to influence other external autonomous system that we don't have like direct administration on. And finally, we have tested that throughout traceroute command, and we saw that how a primary and secondary link could be useful, just in case the primary is down, so the secondary will be used instead. So with that, I conclude my lab and configuration, and we'll see if there's any question or comment.
Well, thank you very much, Ali, for this. I don't see any question, or some questions were already clarified in the chat window. So we're a few minutes early. I want to remind you, this is available, and we're just covering a little bit of the labs that are available. There are also some exercises, as Ali said at the beginning, exercises that are somehow the use case. I remember one use case that Brenna was mentioning, following the longest autonomous system path. So how do we steer traffic? Exactly what Ali was showing here. Thank you very much, Brian. Well, I don't see any questions. So actually there's one, Ali, if you want to read that, or you want me to read and want to address that?
With therefore, or is there a way to configure BGP with just a config file alone instead of the CLI? Yes, it is available, and I can show you that here. So So with FRR and like our topology, if you're using our virtual machine, I think there's this file right here. Here you will see there are, because like we have up to like 30 routers in our labs. We don't use this much of routers, but for every router there is a directory where you will see the configuration. So like this BGP, the configuration is basically here, and it's empty now because we haven't saved the configuration. So one thing you can do after, like, let's say you have configured everything and you wanna save your configuration, you can enter the VTOSH session and you can like write here. So now, because we have we only use BGP and Zebra for the interfaces. So if I click on it again, you will see that the configuration now is committed to the conf file. And similarly, you can use this file to do whatever you want. If that's answer your question. Does FRR have a commit mode? You mean like as in write? As in Juniper?
The answer is I'm not aware, or we don't use commit. Everything that you configure go to the configuration file immediately. Doesn't have the commit. Now, if you want to save in, it's somehow similar to the Cisco router. When you do a change of configuration in a Cisco device, you are writing in the running configuration file. This is what Ali is showing. It's just directly writing in the configuration file. It's going to take, yeah.
Some Cisco, and I don't know if Zebra or FRR does this, but you know, on a real Cisco router, you can do a write, commit, confirm kind of thing, where and specify a time period. So if you really botch the config in 3 to 5 or whatever minutes you set, it'll revert to the old config again. So that's available. Kind of like that would be like Juniper's commit confirm.
Yeah, and we don't, at least we never use FRR, the one that we're using. I don't see this feature. The question from Steve, how were the tools FRR, Zebra, and BGP daemon chosen as opposed to other BGP router tools? When we decide to do this lab library, we were looking for open source that were somehow known by the open source community, and we just found FRR to be quite fit quite well for our project. Perhaps there are others that we might explore, but we just found this to be somehow popular into the open source community. And Steve, by the way, FRR include other protocols. You are mentioning BGPD, which is the daemon for BGP, but it has, when you install FRR includes OSPF, REAP, static routing. So it includes a whole set of protocols already. Okay, any other questions? Well, Ali, thank you very much for this presentation. Again, this library is available. for 3 months, and we can extend and we can make available. Some of you already requested access to other libraries like Advanced BGP. Just let us know if you want to access those, and we will make them available to you.